All right. Check one other thing. So far, it's okay. All right, gentlemen, welcome in. I'm just about done with attendance. We're pretty much done with everything. We have like one more. I'll give you an update momentarily. Let me finish attendance and then we'll do some announcements. This is Lori Beth Denberg with your. I was about to say morning announcements. I know she did vital information. It's an old show. It just ran across my mind. It's silly. Okay. All right. And let me mark these other gentlemen as absent until they show up. Come on. Oh, there's one. Let's see. This one. Okay. Give me just a moment and we're about to get started. All right. Let me just mark these guys. Come on. All right. Cool. Leave that like that. Cool. Okay. So welcome. This is, let me see. Exam 3 is week 12. This is 13. So this is the top of week 14. So we are in the home stretch, right? I think it's only like 16 weeks. I need to kind of confirm some dates and things. So this week is the last week of the new material, right? So today we're going to be working on section 6.4. I'm going to suppress my audio so I can focus. We're going to be working on section 6.4. Let me get this student. He's going to be here. Did I get him on? No, I didn't. Okay. We're going to be working on section 6.4, system of equations in two variables. Yeah, so this is the last of the new material for this semester. We'll do the lecture for today, and then on Wednesday we'll work on homework associated with it as usual. If you have questions or concerns, in the chat, like during class is the best time to kind of reach me. That's the best time. And like again, the real intent of this time is to be like a study session or Q&A, but I just kind of fill it with lecture and like working through the homework. I know we have the Thanksgiving holiday coming up. I think you all do get that Wednesday off. We'll probably meet that Monday. Like I said, I had to confirm some things first. And then I know, like, as soon as we get back, though, it's going to be time for finals. Usually, the final exam for college algebra is that Thursday, the week of finals. Also, for that week of finals, which is the first week of December, I think I scheduled for all of our assignments in Pearson to lock out. All right. So that means old homeworks, quizzes, and exams. You want to get them in order ASAP. Once we hit that Monday, I think it's that Monday at 9 a.m. going into the week of finals, everything locks out. The idea is that when we take the final exam, that's it. When you take your final, that should be it. Nothing else should linger past that. So if you have not already gotten your things on Pearson in order, you want to do that ASAP. However you get it done, just sit down with the tutors, work together. Just you want to get, and if you don't work on anything else, at a minimum, you just want to make sure that your exams are in order because your exams are going to account for like 80% of your overall grade. So once those are in order, that'll be the bulk. Now, if you feel the gumption and you just want to go back and like work on your quizzes and homework, it's not going to hurt you. The real intent of the homework was really just to prepare you for the exams. And so once your exams are in order, that's kind of how we do that. Again, if you have questions, comments, or concerns, you want to use the chat to get my attention. Otherwise, I think we're just going to go ahead and get this party started. Let me check something really quickly. I always check kind of late, but I think it's fine. Okay. Okay, that looks good. So we're going to go like this. So I hope everyone has, I know it's an adventure. I know it's a little different. But that's how that's how these experiences go, right? We have an idea of what it's going to be, and then the application is oftentimes different than the theory, and that's just how life is, right? You make a plan, and then just ready to adjust the plan in the flow and the rhythm. To me, a friend of mine sent me this motivational video over the weekend. It was basically about believing in yourself, and it was saying things like, if you have someone that has sheer talent but doesn't believe in themselves, the minute they get faced with obstacle, they'll stop. But if you can have somebody that has no talent, but if they believe in themselves, there's no limit to what they can do, right? So I just say that to say, to encourage you all to just above anything else, believe in yourself. Know that you can do it. You wouldn't have started on this process if it's not possible. As long as you believe in yourself, you'll be able to do anything, right? Okay. Anyway, so let's kind of let me see. I think this is okay. It's a little bit of a lag, but we'll work with it. So we're going to be working in chapter 6. There's one section in chapter 6 that we're going to talk about as some further topics in algebra. And this is section 6.4, system of equations in two variables. Some objectives here that we like to look at. One, we like to verify a solution to a system of equations. 2, we want to solve a system of equations by the graphical method. 3, we want to solve a system of equations by the substitution method. 4, we like to solve a system of equations by the elimination method. And 5, we like to solve applied problems by solving a system of equations, okay? So let's see. So we have some definitions. A set of equations with common variables is called a system of equations. If each equation is linear, then it is a system of linear equations or a linear system of equations. If at least one equation is nonlinear, then it's called a nonlinear system of equations. Here's a system of two linear equations and two variables, right? So I feel like a lot of that's self-explanatory. Let's keep going to see how this unfolds. A system of equations is sometimes referred to as a set of simultaneous equations. A solution of a system of equations in two variables x and y is an ordered pair of numbers a comma b such that when x is replaced by a and y is replaced by b, all resulting equations in the system are true, right? So this is kind of referring to like what a solution to a system is. A solution are going to be basically two numbers like x and y, or ordered pair a comma b such that when you plug it in for x and y, it makes all the equations true, right? The solution of a system of equations is a set of all solutions of the system. So in this example, we want to verify that the ordered pair is a solution to the system of linear equations, right? In order for this ordered pair 3, 1 to be a solution, then what that means is that when we replace x with 3 and we replace y with 1, it makes both equations true, right? Let's see this in action. I want this dark color, right? I'm choosing like a dark blue. So let's replace x with 3 and y with 1 in each equation and see what happens. So if we consider the first equation, we're going to have 2 times 3 minus 1, right? That's going to be what? 6 minus 1, which is 5. So that checks out, right? And then if we consider the second equation, we say what? 3 plus 2 times 1. That's going to be 3 plus 2, which is 5, and that makes that one true as well, right? So when we replace x with 3 and y with 1, we see that it makes both of these equations true, okay? So then 3, 1 is a solution to the system of equations. Let me see. You guys can't hear me? Okay. Oh, this whole time? Testing. Okay. System. Let's do it like this. Come on. Are you bugging out on me? Okay, I might have to reboot this. let's go here. Force quit. Okay, I'll be right back. New meeting. Okay. Can you guys hear me now? I think yeah. Let's see what's going on. Okay, that looks okay. Let's put this back. Give me just a moment. Input is this one. Output. Not that one, this one. And let's see, let's go like this. Let's share. We want to share this one. Okay. And then, yeah, it looks, yeah, thanks for that notification that you guys couldn't hear me. I think it's like this or like this. So I think I'm going to rely on my recording for our announcements because, you know, I don't know that I can go back and kind of repeat whatever it was I said because I know I will miss something. I think the stream caught the audio. I will check it later. If it didn't, then I'll redo it. So for my announcements, I'm going to rely on my recording just because, yeah, my settings were off for Zoom. The setting was fine for the stream, but I think for you guys, you didn't. I know I realized that you didn't hear me once you notified me. Yeah. Again, I'm just going to rely. I'm going to rely on my stream for like the first part of class, so you're going to have to go back and listen to it, and I'll just try to fill in as we go. All right. I'll try to fill in as we go because I know that in the Zoom call, I know that you guys couldn't hear me. Can you hear me now? It looks like you can because I can see the audio thing jumping. And let's get rid of that. Okay. So I'm just going to kind of continue. So what we're doing today, this is section 6.4, a system of equations in two variables, right? So this was an example of a system in two variables. And so this example asks us to verify that this is the first example. So we really haven't missed much of anything. But again, I would suggest you go back after class and watch the intro and the announcements and everything, so you can get that stuff filled in. So to verify that this ordered pair is a solution of the system, basically, whenever we replace x with 3 and y with 1, it should make each equation true, and you can see where I did that, right? I plugged in x was 3, y was 1, and they made both equations true. So let's kind of keep moving forward and see how this concept of system of equations in two variables evolves or unfolds. So this is just a digital type version of what I just did, all right? And again, in this example, all we were doing was verifying that when that 3 comma 1 was a solution to the system. And so when x was 3 and y was 1, yeah, I don't know what to do about that. Okay, we're going to keep going. When x was 3 and y was 1, it made the system true. Okay. So now in this example, we're asked to use a graphical method to solve the system of equations. So basically, they're asking us to, when we graph these, I'm trying to think if I want to draw these graphs. I mean, I can. It's just a little bit cumbersome because, I need to create the, let's go, that's fine. Let's go view, seamless. And let's do paper. I could just do it in just a moment. I think he was here. Let me see. No, it was his brother. Okay. And I think this will be good. Let's hit done. Okay. Now okay, I think this is okay. Okay, so we're actually solve this system by graphing, right? So we in the previous example, we verified that an ordered pair was a solution to the system. So now again, this is called a linear system of two variables, right? A linear system of two equations and two variables, right? It's basically two linear equations and have two variables. So what I'm saying that to say, we're going to graph these and see how can we solve this system graphically. So let me see. Okay, I think I'm going to try to go 20 in all directions, and we want to plot these, right? So I usually like to start with the origin. Let's go. Let me see if we went 2, 4, 6, 8, 10, 12, 14, 16, 18. I think that's more than enough. So if those are my twos, let me see if I can duplicate this. Copy, paste. Let's see, I do run out of space. Okay, I'll truncate some of them. And I think we'll have enough space for what we need. And then paste. Okay, let's put this down here for right now. So, I don't know if any of you all play like Dragon Ball Z Dokkan Battle, but in this game, there's a hack. Someone discovered a hack, and I first saw it on Reddit. Man, Reddit be having like valid information that I don't be taking serious. But someone first showed it on Reddit, and I was like, oh, okay. Well, I didn't realize what he was doing. But then one of the YouTubers I followed, he confirmed it, and so I tried it out. I was like, oh, this hack is real, and it was super easy to do. So I was like, going through beating all the hard missions I couldn't beat. Then they released something that was like, they tried to use a scare tactic, like anybody using this mod will be banned. I was like, man, get the f out of here. Anyway, it was just a fun little like 24 hours. Okay, I probably have way more than I need. Okay, so I counted by twos, right? So let's do like this. Nope, that's all right. Like this. Okay. And then like this. Let's see. Nope. So like this. Okay, let's undo that. Try that again. That's fine. So this is the positive x over here. In this direction, this is the positive y. Here's the origin, and we went by 2. So this was 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay. 2, 4. And these are negative over here. Okay. Okay. And then okay, and these are negative. Okay. Something saying I should probably duplicate this side because I might need it again. So let's just copy and paste. Okay, we'll use this one. Okay. And then actually, let's use this one because it's right next to this. So let's do, if you're okay, what's someone's favorite color in the chat? Anybody got a favorite color? You guys there? Green. Anybody else got a favorite color? They say geniuses pick green. Anybody know that movie reference? Anybody got another favorite color? Gray. Okay. I'll try gray. We'll see if we can do it. Okay. So let's see. Green. So we'll do the first one in green. So let me see. Let's put it here. We have this. So equation 1. I guess will match. We have this 2x minus y equals 4. That's equation 1. Now there was a request for gray. Let me see if I can get this gray going. There's a gray there. This one is added to favorites. Am I out of space for favorites? Or is it there? Maybe it's gone. Okay. I'm not going to worry about it. And then, so the second one, we'll see. Let's see. We got this 2x plus 3y equals 12. That's the second equation, right? So we'll do the first equation in green, the second one in gray. All right. Okay. So now if I'm going to graph the first one, there's a couple of techniques that we can use. This is a good recap on graphing. We could plot the x and y intercepts. That's one way. We can put it in slope-intercept form, which is y equals mx plus b. So let's kind of focus on the green one. I'm going to work it up at the top though. Are you like freezing on me? What's the deal? Okay. Let me see. Green. Come on. What's up? Okay, give me a second, cause give me just a moment. I'm gonna reboot this. Yeah, it is dragging today. No, cancel. I want to work here. Oh. Okay. So if we have this, man, now it's like lagging, and I don't know why. Usually when I reboot it, that stops that. 2x minus y equals 4. Hang on, let me try one more time. So if I go like that, that's fine. Ugh, technology is like throwing a fit today. Let me reboot this. It's gonna be a minute. Let's go like this. Okay. Let's try to reboot all this stuff. Okay, that's better. And then let's go here, share. We want to share. Come on. This one. Okay. Let's go users. Chat. Okay, cool. Okay. I think we're okay. Let me check one other thing. In here. Okay. Okay. Looks okay. We're going to go with it. All right. So let's try this again. So we have this 2. That's much better. 2x minus y equals 4. So we're going to work this equation one. Like if we solve for y, we add y to both sides. Come on. If we add y to both sides to subtract 4, we ultimately get y equals 2x minus 4, right? You should be able to get there. And then the second one, let me see if it'll allow me to add now. Yeah, there we go. Yeah, I guess it just needed to be rebooted because now everything is working. So we have this 2x plus 3y equals 12. That's equation 2. If we solve for y from here, let me see, I'm going to subtract the 2x from both sides. So then I'll get 3y equals negative 2x plus 12. Then divide both sides by 3. Y equals a negative 2/3 x. What is that? Plus 4. Right? So we wrote both equations. We solved for y in both equations. Now we're going to graph. So if we're graphing y equals 2x minus 4, that means the y-intercept is negative 4. Right? So y-intercept is negative 4. And then the slope is 2. So let me do this really quickly. Let's copy, paste, copy. Okay. So then, let me see. Y-intercept was negative 4, then the slope is a positive 2. So that positive 2, to get the second point, if we go up 2 and right 1, that's not 2, up 2 and right 1, then that gives us the second point, right? And usually, I usually like to just do several points. So then if I go up 2 and right 1 again, basically it's all the points on that diagonal, right? Let's do a few more. It just kind of helps. So then when we draw our line, let me see. If I go all the way, it's going to be from about, it's like here. I lost it. Let me see. When x is negative 4, negative 12. Let's see. 18. What is that? That's negative 18. That's going to be what? Negative 14. So then negative 7. Okay. So about here. All right. Oh, sorry. Let me try one more time. Undo. Okay. So when we draw our lines, idealistically, let me see. Right there. Nope. Is it here? That's better. Is it in here? That looks good. Okay. All right. So we want the line to extend across the whole graph. Right. Okay, that looks pretty good. All right. So that's the green one. So then let's do something similar for the gray one. It says the y-intercept is 4 and the slope is a negative 2/3. So if we put a dot on 4, here, let's undo and paste. And we want that to be gray. And copy. Okay. So for the second one, the y-intercept is 4. And then the slope is a negative 2/3. So then negative 2/3 means we go down by 2 and right 3. We can put a point. All right. Uh-oh, you should see something happening there. Let's do another one. Down 2 and right 3 is here. Down 2 and right 3 is like here. Okay. So then what I'm going to do is draw my line. So what I'm going to do this time, I'll do a little bit different. I'm just going to draw the line and then come back and move it around, because we're working in a digital. Okay. Okay, that looks decent. Okay. Nope, that's still off. Okay, let's see. When x is 18, hang on, I'm trying to find that exact number. when x is 18, 18 divided by 3 is what? 6 times 2 is 12. Negative 12 plus 4 is negative 8. Okay, so that's this point. And then when x is, let's do when x is negative 14. Let's do when x is negative 15. So that's going to be what? 5 times 2 is 10, plus 4 is 14. So that's going to be like here. 15 is here. That's much better. Okay. Because I was trying to like eyeball it, and that's what was giving me a hard time. So I was like, okay, let me find those exact numbers. So I'm not trying to eyeball it. Come on. Okay, there's that one. And then this one. What's the time? Okay, that's fine. Okay, so now, that was an adventure, just trying to graph. So we got it. We finally eventually got it, okay? So when we graph these two equations, these two system of two equations and two variables, system of two linear equations and two variables, we get these two graphs, right? But notice they cross, what point is this? X is 3. They cross at the point, what is this? 3, 2, right? So the suggestion is, or the claim is that the ordered pair 3, 2 should be the solution to the system, right? So you saw us graph it. They cross at the point 3, 2. So then the claim is that if we plug when x is 3 and y is 2 into the original, then it should make both of these equations true. So let's check. I'm just going to write it here. We're going to check, right? So if we say 2 times 3 minus 2, that's going to be what? 6 minus 2, which is 4. So that one checks out. Okay. The second one is what? 2 times 3 plus 3 times 2. That's going to be what? 6 plus 6, which is 12. That one checks out as well. Okay. So then the order pair 3, 2 made both systems true. So then the order pair 3, 2 would be the solution to the system, right? And the only reason I kind of like took the time to graph is because, you know, we're live streaming. So then I could like always rely on that time. I'm still going to let you guys go in just about 10 minutes. But I'm just using the fact that we are on a live stream to my advantage. Let's go paper like this. I don't know if you remember last time I was using this and I mentioned something about, let me check and see if they did the update they needed to do. Now when I got on today, what I was looking for was actually there. So they actually did the update, which I thought was interesting. It was kind of weird because I was like, damn, are they like listening to me? Like responded directly to my inquiries and requests. Okay. And this is just a blank one. Make sure you guys can hear me. Testing. Okay, and I'm gonna suppress my audio. Okay. So here's a type version of what we just did. Use the graphical method. So graph both equations on the same coordinate axis. One technique is you can find the intercepts of equation 1, and they plotted the x and y intercepts, and that's how they did it, and that's totally fine. All right. So then find a point or points of intersections of the two graphs. So where did they cross? These just happen to cross at the point 3, 2. So then that was those. Right? And then you check, right? So you want to check that the order pair 3, 2 works. Okay, let me get this student. The heck did that light lock out too? He might be denied today because I don't have. Yeah. Yeah, everything's kind of messing up today, so I'm not gonna worry about that right now. Cause we're almost done. We only got like 2 minutes left. He'll be okay. He's gonna have to wait. Okay. All right. So we verified that those work. So now we have. See, like in good conscience, I can't like not get this student. It's like irking me. Let me see. Yeah, he's gonna have to wait. Okay. So next we want to look at the solutions of a system of equations. All right. So some solutions. The solution set of a system of two linear equations and two variables can be classified in one of the following ways. So we could have one solution, which is like what we just experienced, where the system is consistent and the equations are said to be independent, right? So this is an example where the system is consistent and the equations are said to be independent. So then next we have, this is an example where there's no solution. The lines are parallel and the system is inconsistent, right? So there's no solution. The lines never cross, so you never get a point of intersection, so no solution. And then the third case that we might encounter with linear systems, we have infinitely many solutions. These are basically two or more lines that are on top of each other. So the lines coincide. The system is consistent, which means they're a solution, and the equations are said to be dependent, which is like basically one equation is like a multiple of the other, right? But it's like one equation is on top of on top of the other. Let me take a moment to try to log back in so I can get the student. If I go here like this, yeah. And like usually I have that stuff ready to go, but everything was just like going haywire today. So come on, what's this class? Come on. And then this one, attendance. And we have this one. Cool. Okay, I got them. Okay. So again, with infinitely many solutions, that's basically one line is on top of the other. Another way you might see it is that like one line is a multiple of the other. The line, this is like where the lines coincide. We said that this system is consistent, which means that it has at least one solution, and the equations are said to be dependent. So that's like, again, I know it is like one equation is a multiple of the other, or you have infinitely many solutions, right? So here we want to see some algebraic methods for solving a system of equations. We first in the first example, we verify a solution to a system, right, by plugging in the x and y. Then we saw one method for solving a system in a graphical sense. So when you graph the two equations on the same coordinate axes, wherever they cross is going to be the solution or solutions to the system. So now we want to explore some algebraic methods for solving the system of equations, right? So we're asked to solve this system where we have these two, and we're using the substitution method. So in the substitution method, what we're going to do is solve one equation for one variable, and then we take that and plug it into the other equation, right? I think I have enough space, so I'm going to work with the space that I have. I'll use this dark blue. So we want to solve for one of the variables in one of these equations. To me, equation 2 looks like the easiest to solve for like y, right? So I'm going to solve for y in equation 2 and then take that and plug it into equation 1. So from equation 2, we have y minus 2x equals 9. All right? If I'm solving for y, add the 2x to both sides and we get y equals 2x plus 9. All right? So then what I want to do is take that y and plug it in for y in equation 1. So one rule of thumb is whenever we're solving system of equations, every time you have an unknown, you need an equation. We have two unknowns, namely x and y, so that's why we have two equations. So every time you have an unknown, you need an equation. All semester long, we've been working in one equation and one unknown. All right, so now we're considering more than one unknown. Again, every time you have an unknown, you need an equation, generally speaking. Okay, so we're going to take this and plug it into equation 1. So we have 2x minus 5 times y equals 3. But in this case, the y is the 2x plus 9, right? So now at this stage, we have one equation, one unknown we can solve, right? So now if we just do our algebra, we can distribute this negative 5. We'll get 2x minus 10x minus, what is that, 45 equals 3. I'm just going to kind of continue like here to the side of that. 2x minus 10x, I guess I'll work over here actually. I'll put this like here. 2x minus 10x is a negative 8x. If I add 45 to both sides, I get what, 48? Divide both sides by negative 8, x equals, what is that, negative 6? Yeah, I think that's okay, right? So now we solve for x. Now we need to go back use this to solve for y. So I'm gonna, we have an equation where we already solved for y, so we have the y equals 2 times x, in this case x is -6 plus 9. So then ultimately get y equals, what is that, -12. So what is that, -8? That's not right. -12, what is that, -3? Yeah, -3. I don't know where I'm getting it from. So then our claim that the solution to the system is going to be the ordered pair -6, -3. Okay, let's just check these really quickly by plugging them into each equation to see if they do or do not work. Then I'll probably let you guys go, and I'll probably keep streaming because it's not a smooth, clean stream, but I want to use it. So let me see. When x, so 2 times -6 is -12 plus 15 is a +3. -3 plus 12 is 9, right? So when we plug in the order pair -6, 3, it makes both of these equations true. Okay. So this is us doing it by hand. Then I think we have a typed version of everything that we just did. And then -6 and -3, you see it there. Okay. Okay, we're actually solve the system of equations. So we did what? Oh, let me see the time. I think we got time to do one more before I let you go. So we can use the substitution method again, right? Solve the system of equations. So I'm going to solve for y in the first equation. If I solve for y, if I subtract x from both sides, in that first equation, I'll get y equals -x plus 3, right? Then if I'm doing the substitution method, I take this and plug it into the second equation. So then we'll get this 2x plus 2y. No, back it up. So we just found that y to be -x plus 3 should equal 9, right? So now we have one equation, one variable now we can solve. So we can distribute this 2. We get 2x, let me see, what is that, minus 2x plus 6 equals 9. A number plus its opposite, these add to 0, right? If we subtract 6 on both sides, we'll get to a point where we have 0 equals 3, and this is false, right? This is false. So when you're solving a system and the variables cancel out like that, and you finish with a false statement, this is an example of an inconsistent system, right? Right here. This is an example of an inconsistent system, which means that there's no solution. So, wait a minute. Multiply by 2, right? Yeah, these are parallel lines, right? So they have the same slope but different y-intercepts, right? So if we were to graph these would be two parallel lines that have different y-intercepts. So that means they'll never cross. So that's why there's no solution, right? So this is an example of an inconsistent solution, inconsistent system. We would say no solution. There's no solution. Right? No solution. Or we would say the null set or empty set. Basically no solution. See two parallel lines that have different y-intercepts. Okay. So let's do something similar here and see what happens. Let's solve. We can still do the substitution method, right? And for me, it looks like in equation 2, it'll be easier to solve for y. So I'm going to add y. Oh, let me see. I think we still got time. We got a solid 5 minutes. I'm not going to keep you for that full 5 minutes. At least that's not my intent. But I think we got time to do this one. If I solve for y in equation 2, if I add y on both sides and add the 6, from equation 2, we'll get y equals -2x plus 6, right? So that's from equation 2. I solve for y. Then I take this and plug it into equation 1. We have 4x plus 2 times y, which is -2x plus 6. That should equal 12, right? Now if we solve, now we have one equation and one unknown, so we can solve. We have the 4x minus 4x plus 12 equals 12. Notice that these add to 0. If you subtract 12 on both sides, we'll finish with 0 equals 0. Notice this is true, right? So we have infinitely many solutions, right? If we have infinitely many solutions, all the solutions of this system are going to take on the form, no matter what x we choose, y is going to take on the form negative 2x plus 6, right? So we have infinitely many solutions, and they're all going to take on this form here. Any x that you choose, the corresponding y is going to have that form. Right? Just for the sake of time, I'm not going to check it. I'm just going to use, for instance, like when x is 0. When x is 0, y is 6. So if we plug x is 0 and y is 6, it should make them true. This is gone. 6 times 2 is 12. That checks out. This is gone. Negative 6 equals negative 6, right? You can choose any value for x. It'll output the corresponding y, and it should work, right? So long story short, when you're solving a system of equations and all the variables disappear like there, and you finish with a true statement, that's an example of a dependent system. So basically, one line is a multiple of the other. If we take equation 2 and multiply all the terms by negative 2, we'll get equation 1, right? So one equation is a multiple of the other. Okay, let me just glance at the type version. Equation 0 equals 0. The equation 0 equals 0 is true for every value of x. Thus, any value of x can be used in this equation for substitution. So the solutions are the form x comma negative 2x plus 6. Blah, blah, blah. Same thing that we got, right? Okay. So let me see. We still have about 15 more slides, but I'm not going to keep you guys because that's our time. I'm going to go ahead and release everybody, and I'm going to keep streaming and just use the stream for the rest of the day. For the announcements, I definitely recommend you definitely go back and watch the stream and listen to the opening announcements. Basically, I was just, this is like the last of the new material with this section. I know we got the Thanksgiving holiday coming up. That might be like next week. I'm totally out of sync with the time. But all these announcements are in the opening of the video, so I will go back and watch it. And I'm going to use it later. I'll check it later. If it's not there, I'll make a new one. Okay? So if there aren't any burning questions, I'm going to let you guys go, and I'm actually going to continue the stream. Okay. So, and let me suppress my audio. So then in this example, okay, so now we saw, so thus far, we saw how to verify a solution of a system by plugging in, and we've seen several examples of that. Then we looked at it, we saw how to solve a system through graphing. So we graphed two lines, and where they cross was a solution. The third thing that we explored was solving a system with the substitution method, right? Where we solve for one variable and then take that and plug it into the other. So now we want to look at the elimination method. This is, I want to say, the last one that we have. There might be some others, but the elimination method for solving a system of equations, right? So with this technique, what we want to do, we want to multiply each term of one equation. Like, first we want to choose a variable that we want to eliminate, right? So looking at this, to me, it looks like, cool. To me, it looks like it'd be easier to eliminate the x. Well, actually, I think I'm gonna eliminate the y, right? So I'm not dealing with so many negatives. So I just chose which variable I want to eliminate. Now to eliminate that variable, we're going to multiply each equation. The goal is to get the variables to be the same number with opposite signs by using multiplication. We can multiply each equation by a non-zero real number and preserve the solution, like it won't affect the solution. So again, the goal is you choose a variable that you want to eliminate, and you're going to multiply each term by some non-zero real number. And the goal is to get both equations to have the same. We want that variable to have the same number in both equations, but have opposite signs. One's going to be positive, one's going to be negative, right? So I'm choosing to eliminate y because the signs are already opposite. So now I'm going to multiply each equation by a number so that those y's become the same number. For instance, I'm going to get them both to 12, right? Because it's the least common multiple between 3 and 4. So I'm going to multiply the first equation by, 4. So I'm going to say, like, basically I'm going to multiply this by 4, right? And then the second equation I'm going to multiply by 3. Right? We're going to distribute a 3. into all these terms, right? So then when we do this, the following happens. I'm actually going to work over here as well. So now when I multiply the first equation by 4, we get 8x plus 12y equals, what is that, 84? And then the second equation by 3, we get 9x, 4 times 3 is minus 12y equals 69, all right? 69. Okay. So now we achieved our goal. We got the variable to be the same number with opposite signs. So now what we want to do is add the two equations together. When we say equation 1 plus equation 2, the y's are going to cancel out, and then we can solve for the remaining variable, right? So if we add these two equations together, 8x plus 9x is 17x. 12y minus 12y, that adds up to 0. So number plus its opposite is 0. Let me see. It's a 3, carry the 1, 9, and 6 is 15. 153, right? So now if we divide both sides, I'm going to move this over just because I can. So if we divide both sides by 17, x equals, let me see. I know she's not going to show it here. Hey Siri, what's 153 divided by 17? Yeah, let me see if I do like this. What's 153 divided by 17? 9, right? My Siri is linked to the HomePod. She's in the other room. I mean, I could get her to talk, I guess. Let me see if I do like this. I'm just trying to get to the HomePod. This one. Yeah. And blast the volume. I'm trying one more time. Okay, this might be kind of loud. I hope I don't disturb people. Hey Siri, what's 153 divided by 17? Oh, I can't hear. Okay, I'm not gonna worry about it. All right. Okay, it's okay. Yeah, I don't know how to, because like with the connectivity of like the Apple devices is nice, but like in this case, I wanted to show my stuff on the phone, and it defaults to the HomePod, and I'm like, that's not what I want. So I hadn't figured out how to. I know I could manually do it, but I want it to like be a natural flow where I don't have to like go through and change the settings every time to make it do that. But anyway, you live and you learn. We'll figure it out sooner or later. Okay. So now we were able to solve for x. We got the x equals 9, right? 90 plus 63 is 153, okay? So then we can take this and plug it into either equation to solve for y. Let me see if x is 9. I'm going to use the first equation. So I'm just going to kind of work over here. So if I'm using the first equation, and x is 9, so we're going to have 2 times 9 plus 3 times y equals 21. So that's an 18. If I subtract 18 on both sides, we get 3y equals, what is that, 3? Divide both sides by 3, y equals 1. All right? So then our claim is that the solution to the system is the ordered pair we got 9, 1. So ordered pair 9, 1. Right? This is the solution to the system that we got. Okay, so then we just want to check, right, before we just accept it, right? So when x is 9 and y is 1, let's see. 9 times 2 is 18, plus 3 is indeed 21, so that one checks out, all right? And then the second one, 9 times 3 is what, 27, minus 4 is 23. That one checks out as well, right? So that was a showcase on the elimination method. Man, I like streaming and being able to do this in one go. We had a little bit of technical difficulty earlier. I think I'm gonna just go with it. Like it's okay. Everything can't be perfect. Here's a type version of what we just experienced, and then you see they got the same solution that we got, 9, 1. Right? We're almost done. 2 more. Okay, so this is an example on solving a nonlinear system by a linearization substitution, right? So at first glance, you're looking at this, you're like, man, we got these fractions and the variables and the denominator. What's going on, right? So we're going to transform how this looks into something that we're familiar with, right? So instead of working with 1 over x and 1 over y, this is called a linear substitution, linearizing substitution, right? So instead of working with 1 over x, I'm going to let me see. So let 1 over x, we're going to let that be u, right? And then we're also going to let's kind of get these to be consistent. I'm using that one and this one, right? And style, this one, okay. So then we're going to let 1 over y, if that's u, we're going to let this be v, right? Okay, so now we're going to replace all the 1 over x's with u and the 1 over y's with v. So we're going to have 2u, that's fine, plus 5v. I think this is fine. Let me see, am I doing this right? Equals -5. And then we get, for the second part, we get 3u minus 2v equals -17. Okay. So now this is similar to what we were doing before. All right. So let's do elimination method. Let me see, which looks like it might be easier to get rid of. Okay, I think I'm going to get rid of the v. I'm just choosing whichever one I feel like is easier. I'm just choosing it just based on how I feel, right? So with the v, if I want to eliminate the v, the goal is to get the v's to be the same number with opposite signs. So I felt like to get them both to 10 should be fairly simple. What I'll do is multiply the first equation by what? 2 and the second equation by 5. So I'm going to say this equation by 2, distribute that 2. I'm going to say this equation by 5 and distribute that 5. Okay. I'll continue working over here. So now if we do that, we get the following. We get 4u plus 10v. And see, that's why I use the colors, because sometimes my handwriting is not super clear. And so the colors help to distinguish, keep track of everything. Equals -10, right? And then the second one we multiply by 5. So that becomes what? 15u plus -10. Oh, so that's a -10. -10v. 50 plus 35 is 85. Okay. All right, so we achieved our goal. So now if we add these two equations together, the v should cancel. I'm going to bring down my equal sign. 4 plus 15 is 19u. -95. Yeah. What is it? 5. 50 plus 45 is 95. So then u looks like it equals what? -5. Okay. Kind of running out of space. I might need to give myself some more space. I'm going to work with what I have for right now. And what I'll do, I'm going to shrink. I can shrink all of this. Let's shrink this down. Here, let's do from here to here. I just want to shrink it down a little bit. Boom. Okay. And I'm going to continue working over here. Okay. So then we want to go back and find v. If that's a -5, I'm going to plug this into the second equation. So then, oh, wait a minute. If that's a -5, actually I'm plugging it into the first one. So then 2, the u was what, -5? So 2 times -5 plus 5v should equal -5, right? So then that's -10. So then we get like -10 plus 5v equals -5. Add the 10, so then 5v, come on, is what, 5? So then v equals what, 1? Because you divide both sides by 5, v equals 1, okay? So now, we got our u and our v, so then we need to go back and find x and y. So if u is 1 over x, so that means that 1 over x equals -5. So if you cross multiply, you get what? X equals -1 over 5, right? Okay. And then for the v, we got 1 over y equals 1. I hope this is okay. I'll check it. You know, we'll find the error if we made a mistake. Let me look at something really quickly. Now u we got -5. 2u plus 5v equals -5. -10, that's a +5. You get 1. Okay, let's just go with it. So then y equals, we get y equals 1, right? So these are the, so we got x is a -1 over 5. Let me check it one more time. Wait a minute. Yeah. Let's go with it. Okay. So now the ordered pair that we get as a solution, we get the ordered pair partial. It's fine. Cut it right there. Okay. We get the ordered pair -1/5, comma 1 as a solution to the system. So then we just need to check and make sure that it works. Style. Okay. Okay. So let's see, how do we do? Let's see. I should kind of get some more space, but I'm going to just try to work with this. So if x is a -1/5, if we plug it in here, that becomes what, -10? Okay. Plus 5 is -5. So that one checks out. Okay. We plug in x is a -1/5. That first part becomes -15 minus 2 is -17. That one checks out as well. Right? So then, yeah. So that's an example of linear substitution, linearizing substitution. We're still doing substitution. Well, we did substitution and elimination together, right? Because instead of working with that fraction 1 over x and 1 over y, we linearized it. We transformed it. And we said let 1 over x be u, 1 over y be v. Made those substitutions. Now we transformed it into like a linear system of equations in two variables. So then we used whatever method we preferred. I think we chose the elimination method. And then we solved for u and v. Then we took those results for u and v and transformed them back in the proper form of what x and y would be. So we got u was -5. When we transformed it back, then we got the -1 over 5, and a similar story for v, right? Okay, that was an adventure. Okay, let's see. So then we have a type version of what we just did. Solve the system, replace 1 over x by u, 1 over y by v. I think they did the same thing we did. They eliminated the u, right? Which is fine. They got v was 1, that's fine. And then u was a -5. Yeah, so we got the same thing. And we checked. Okay, let me see. We're almost done. I think this might be the last example. Find the equilibrium point if the supply and demand functions for a new brand of DVR. Man, you can tell this is outdated because, I mean, I guess people still use DVRs, but we're clearly going into like streaming. I haven't used a DVR. I know my mom does, but I haven't. But anyway, like most of my stuff is like Apple TV and you know devices like that, like streaming stuff. And I don't even really download anymore. I used to, but it's not really necessary. I was like, I don't know. Anyway, find the equilibrium point if the supply and demand functions for a brand new DVR digital video recording device are given by the system, right? So it says where P is the price in dollars and X is the number of units. So you have the price of the unit versus the number of units produced and sold, right? Supply and demand. So these are supply and demand equations. Okay. Oh, okay. So if we're going to find the equilibrium point, basically we want to see where these two equations cross. So they're basically asking us to solve the system of equations. So now notice that for equation 1 and equation 2, they're already both equal to P, right? So we could just kind of set them equal to each other. If the first equation equals P, the second equation equals P, then you can set those two components equal to each other, right? Let's see how that works out. So then I'm going to do 80 minus 0.0008x should be equal to 60 plus 0.0012x, right? So now we have one equation, one unknown we can solve. We can add that 0.0008x to both sides and subtract 60. Let me see. What is that? 0.002? So if we add the negative point, if we add the 0.0008 to both sides, we'll get 0.002x equals, so I added that, and I subtract 60 on both sides, we get 20, right? I kind of switched the order around just so I can have the x on the left-hand side, right? But what I did, I added the 0.008x to both sides, and I subtracted 60 from both sides. And then you eventually get to something like this. So then, this is the same as, so then if we solve for x, we want to divide both sides by 0.002. So then x is going to be equal to, let me think about that. That's the same as 2 over what, 1,000? So if you divide by 2 over 1,000, it's the same as multiplying by 1,000 over 2. So 10 times 1,000 is 10,000. All right, you can use a calculator. So our claim is that the equilibrium point is going to occur when we produce and sell 10,000 units, right? Then we need to see, well, at what price should we sell these, right? So we need to plug this x into one of the equations. We're going to move it, what, 4 times? I'm going to plug it into the second equation because I feel like that one might be easier. I'm going to work with this space over here. So if we let x be 10,000, then the price is going to be 80 minus. Now, if we move this decimal, we have 4 zeros, so we move the decimal 4 times. 1, 2, 3, 4, right? So it looks like it's going to be 80 minus 8, and so it looks like the price should be, what, $72, right? So then our claim is that the equilibrium point occurs when we produce and sell 10,000 units, each sold for $72. Okay. I swear the Thanksgiving holiday totally snuck up on me. And like folks already got Christmas decorations out. I'm like, come on. Don't you think it's a bit early? I personally don't like subscribe to like the commercial aspects of these holidays. I try to use the energy just for like togetherness and oneness and family and unity and all that kind of stuff. And you know how we should be like year round. But I just refuse to, you know, submit to the commercial aspect of it all because it's like I think every month there's a holiday or some way that you're expected to spend money, and it's like we're not making each other rich, we're making other people rich. I'm like, I'm tired of making other people rich. Like, can we make ourselves rich for a change? Like, that's what my mind has been. Okay. So substitute the value of p from equation 1 into 2 and then solve the resulting equation. X equals 10,000 units. To find the price, back substitute this into one of the equations, you get 72, right? So the equilibrium point is 10,000, produce and sell 10,000 units sold at $72 each. You can verify that this point satisfies both equations, right? So we have supply versus demand. Okay, I think that's it. It wasn't that much more. It's always like that. That's why I try to keep going. Shy of like the technical difficulties we were having earlier, you know. Let me do a quick little recap. So the announcements that I did earlier. So this was officially the last of the new material. Um, there's not anything else that I want to discuss as far as new content for this semester. Um, I think we have the Thanksgiving holidays next week. I had to check those dates. We probably meet on that Monday, and then I'm pretty sure you guys have that Wednesday off. But as soon as we get back, it's going to be time for finals, all right? And then another thing I mentioned was that Monday, that first Monday of December going into finals, I think all of our assignments on Pearson are going to lock out. I think that was the date I set, was that Monday at 9 a.m. So if you have, you just want to make sure that your Pearson is in order, right? Make sure that your Pearson is in order. And if anything, if you don't do anything else, you just want to make sure that your exams are where they need to be, because your exams are going to count for just about 80% of your overall grade. So if you don't do anything else, at least if your exams are in order, then you should be positioned for success. Okay, so if there aren't any burning questions, we're actually going to end the session here. Okay, and from one beautiful mind to another, enjoy the rest of your day. Peace. Take care, guys.